high efficiency units and where they start and how they absorb the heat. Typically, there's going to be two heat exchangers on these. One is going to be our primary heat exchanger, and that's going to be this looping one. Sorry about that. And that's going to be the pipe that comes down this way. This is going to be our primary heat exchanger. Then it goes into a radiator coil, so it's a much narrower tubing, kind of like an air conditioning coil that goes on there. And that's going to be absorbing the secondary one. Now, all the condensation that's going to be created in here, because these are condensing furnaces, so they are going to be creating water or condensation, that's going to settle down here. And if it can't drain out, it's going to actually very corrosive. I forget if it's alkalytic or acidic, nor does it really matter. It's going to start corroding the heat exchanger, and then we're going to start getting drips coming down to the floor. All right. Yeah, it's looking on the floor when these things are running, see if it's wet. Just a telltale sign. So as the air runs up where the blower fan is, it's going to be room temperature. It's going to absorb most of its heat through the secondary heat exchanger. And then as it gets up higher and higher and higher through the primary heat exchanger, those pipes are going to get hotter. So then as the temperatures equalize out, that's how it absorbs. That's how it absorbs as much heat as it does. And that's what this drawing here is trying to show. So it's colder here on the outside and everything starts getting warmer. It's hottest here and it starts losing the heat as it gets colder. And basically how a high efficiency can be so efficient. Things that we want to look for. All right, we know we're going to create a lot of condensation, so we need to collect and drain that condensation properly. You're going to find that a few different areas where they collected, those things do crack, whether it's from temperature changes or whatever, so because of which they leak. Look for the water, look for the rust, look for all the problems where the tubes are disconnected. We don't use neutralizers in our area. I've never run into one anyway, and it should go into the floor drain. If there's some reason in your area that you become aware that you do have to use a neutralizer, that's what the tank is for on the bottom. I don't know what you would put in there and how often you would have to put it in there, but just know what it is, all right? Temperature rises, to me, are the most important thing that you could do, all right? So taking that thermostat or thermometer, dial thermometer, turkey thermometer, whatever, and getting that temperature rise and making sure that it matches the data plate, that's huge. All of our vents, our plastic pipes that are connected, everything should be tight and secure. I shouldn't have any stains that are coming out of these things. If it's orange or yellowish in any which way, that usually means that something is leaking out of that pipe. So they are supposed to be sealed airtight and watertight. No water, no air should expel from these. Heat switches, so they do have high limit switches on there, pressure differentials we talked about, and then the blower door interlock. So just about every door or every furnace that has a blower fan should have an interlock switch on them. I have seen them bypassed quite often. There's a lot of heating contractors that will just put tape on it to bypass it. That way if the door comes loose, it doesn't shut itself down and people don't get a service call. I get it. And makes sense. But I am not a fan of bypassing any safety device whatsoever. In our line of work, it's the calls that you get were, why didn't you tell me? They all begin with the same magic words. Why didn't you tell me this? All right. And the real truthful answer is because I really didn't think it was that big of a deal, But it's not up to me. It's up to my clients. So I could let them know what it is. I could let them know the rationale behind it and let them make their own decisions when it comes to it. I'm not a believer in trying to convince someone to take the tape off. I want to let them know the argument that the person put it on there because sometimes the doors aren't sitting tight and that the furnace will shut down and you're not going to know why it shut down. You're going to call the heating person and you're going to be upset that there's a $150 or $250 service call just because the door was loose and you didn't recognize that. And I told you to take the tape off because it's dangerous, all right? I just can't do that. And I'm totally fine. If somebody disagrees with me and you think that's a big deal and you should put that on there as well, that should be your choice or the client's choice. Me personally, the reason it's there, if I take that door off, I don't want to have a chance for that blower fan to kick on and me to be working anywhere near it and get sucked into it. That's the main reason. So here they're talking about the differences in temperature rise between older furnaces and newer furnaces. Most high efficiencies you're going to find are going to be somewhere around 25 to 55 degrees. And most of the older furnaces, those are going to be like 55 to 85 or, 65 to 95. I've seen them up there pretty high as far as the temperature differential that comes in there. So we use less energy, we use less BTUs because we absorb a higher percentage of the heat that we use. So we can use less gas and save more money. That's the whole purpose of the high efficiency. Going back to that though, if the whole purpose of having the high efficiency is to save the energy, then why would I want to take conditioned air from inside the house, use that to make the fire, and then just blow it outside the house? I'd rather get my combustion air, from outside the house and then blow it back to the outside. Charlie's 2 cents. So another term I want you to be aware of is something called orphaning a water heater. So in this one we have the round clay tile. That's where the furnace and the water heater originally went into. They ended up going with a high efficiency furnace. We can only see the pipes along the top on this one. All right. And so that's what these white pipes are up here. And then they ended up putting the vent connector going into the flue. Now, we can't use that big round clay tile for this many BTUs. So that, I think it's like a 3 or 4 inch vent connector that goes in there. Then that connects to a corrugated stainless steel. And I think the next slide shows it good. It really shouldn't even enlarge like it did here. They should use a smaller one so it's the same size going all the way up. But then this is what's called a flue liner that goes through the chimney and all the way out through the top. All right. So every mid-efficiency furnace that goes into a chimney, every high efficient or every water heater that goes into the chimney by itself, they should all have flue liners. That's my 2 cents. And I'm going to call every single one of them that doesn't out. All right. The only ones that were allowed to go into these things were going to be the old natural draft furnaces, and we just don't see that anymore. Now, I hear a lot of arguments from heating contractors where you're allowed to discharge a mid-efficiency furnace if the fireplace is completely inside the house. So it's not on an outside wall. If it's completely inside, you could do that. Fine. All right. That may be true. I would have to see the manufacturer's installation instructions for that particular furnace. I would want to know. But if you're going to go that route, then you're also going to want to send a camera up that flue liner, because these clay tiles, when they had all that moisture and the temperature changes going on and off, they were just known to be cracking and mortar falling out of them. And now you got gaps in there that are going to let carbon monoxide enter the house. And I have been on a few homes where somebody put a brand new furnace in there. It was a high or a mid-efficiency furnace that was in there, because of which the drafts moved slow. In fact, they weren't even enough heat because they put it into the old clay tile, couldn't get it all the way up and out. They didn't size it properly. And then all that carbon monoxide got stuck in there, and that was coming back into the house and was setting off the carbon monoxide alarms. All right. That was a big deal. And then we ended up tracing everything back to the furnace where it came by there, and all they had to do was drop a liner in here. Now, these liners aren't cheap. They look cheap, but they're not. Typically, you're looking at around $1,500, and this is the year 2020. I don't know how long this video is going to be around, and prices do go up. It's been pretty consistently, so I don't know where they're going to be in the future. But I do want you to know what a flue liner looks like, and again, it goes through and all the way up and out of the chimney. It's kind of a no-brainer. You see all that scorching in one spot. Hell, look at the size of that pilot light on there too. But nonetheless, this was a definite hole in the heat exchanger, and every time that blower fan kicked on, it was pushing the air out of the burner chamber. In this case, it was actually backdrafting there. Most of our backdrafting is going to occur at the top where the draft hood is, not down here. This is typically going to be flame rollout. But when you have such a isolated spot, it's that particular heat exchanger in that burner that was doing all the damage. It was, and you can see how, when fire grows or heat spreads, it goes up and out. So that's what we call the point of origin. And you can follow that V as it comes back in there, and that's going to show where everything is starting from. So here's another shot of a heat exchanger, a little diagram. We can see where our burners are going in. Heats up the inside. This is typically how the old Lennox natural draft heat exchangers were. They would go kind of like a hula back and forth, and the heat would bounce off of the different sides before they come back up in there to go ahead and create it. And it's that opening where the burner comes in that you look right on the underside of that, and that's where you find it. But again, we just don't see these anymore. I do want you, to realize that the circulation air blows on the outside of the metal, where the bad gases are on the inside of the metal. All right, going back with my airflow. So this is, and it doesn't matter if it's updraft, downflow, horizontal, I don't care. The order of flow is always going to be the same. Filter, fan, heat exchanger, and then at the top on the right picture is where my air conditioning coil would go if it was there. On the left picture, downflow furnace, filter, blower fan, heat exchanger, and if I had an air conditioning coil, it would be down at the bottom underneath the heat exchanger. We don't want to have our air conditioning coil before the heat exchanger because that air conditioning coil creates a lot of condensation as well when it's running, and we don't want to blow that humidity over our heat exchanger because that's going to cause it to corrode and rust out faster. Same thing, horizontal, left to right, filter, fan, heat exchanger. If I had an air conditioning coil, it would be on the right. All right. Having these things operate and depressurizing a room, it does happen. It is rare. This is mostly going to be a problem on a natural draft furnace, not so much on a high efficiency or a mid efficiency furnace. But what we're talking about, and maybe the next slide will show this. Here's the blower door switch on this one. This blower door switch was just bypassed, and I do this. I take that door off and make sure the furnace shuts down. Just because the switch is there doesn't necessarily mean it's a problem. So going back to where that door was off and the blower door switches and the problems of depressurizing a room that I was talking about, this is the slide that I was kind of getting to. So if we look at this drawings on here, and this was an actual home. It was taken a long time ago, natural draft furnace. What's a common solution if you make the ductwork too small and you're restricting the airflow coming back to the rooms, and when I mean ductwork, I'm talking about the return ductwork, all right? Then that blower fan depressurizes that ductwork and causes them to collapse. And usually the fan builds up speed slowly, so the sucking in part is not as noticeable. But then when the fan turns off, you hear that big whoomp, and that's all the ductwork's coming back in there. So solution to that, and not a very good one, but it is a solution, is somebody can cut in those openings that we're seeing on the return duct where those two red arrows are pointing at. And that way we're not going to depressurize the rest of the ductwork. But then again, we're also not pulling air out of those rooms either. All right, so that's going to make the air circulation from the rooms less efficient as well. I know the solution is actually expensive, which means putting in bigger ductwork or additional ductwork in there, and that's not something that people normally want to spend. So they try to go ahead and find a solution. But here, in this situation, we're in a room where we were depressurizing that room. Now, if you look at the green circle, you can see all the corrosion and rust, and that negative pressure in there was causing this furnace to backdraft. And not only are we backdrafting, but now we're pulling all that carbon monoxide right into our circulation air, and we're just putting it into the house. This house did have a carbon monoxide alarm in it. It was going off. And this is what we determined to be the cause of that, is that the furnace was backdrafting and it was pulling the carbon monoxide into the circulation air until eventually it set off the carbon monoxide alarms. Clearances around most furnaces are going to be pretty much 0 or 1 inch, so they could be put into a tight box. Natural draft furnaces or mid-efficiency furnaces with open burners in the front of those burners are typically going to be 6 inches, all right? And there's going to be a little chart on there where it talks about the left, the back, the front, the right, and so forth. And they talk about how many inches of separation. So this one, the very top of the furnace, they want you to have 1 inch. The front of it, because it's going to be a natural draft furnace, they 6 inches so we don't block the air coming in there. Where it says vent and it says number 6, that's because it's gas. They're really talking about 6 inches around the vent connector for combustible materials, and then we could actually be touching the back and the sides to combustible materials. Here's another one, same thing, sides 1 inch, back 0, front 6 inches, 6 inches around the vent or the vent connector, and the top again 1 inch. All right, just want to know what all those numbers are for. Top 2, front 6, vent 6, rear 1, side 1. Different furnaces have different clearance issues, the combustibles. All right. We see this a lot in condos in the city of Chicago, and I don't know what to say with this. It's an old joke that Corey kind of told me about, and we kept it up there. It's called the Chicago squeeze. We're talking about the suburbs. They sell houses by the size of the square footage of the home. I swear that in Chicago, because they're all smaller and confined, that they're actually selling houses by the size of the square inch. So they do everything that they can to get as much space as possible. So they just compact all the utilities that are in there. But, let's use a little common sense here. I got a gas pipe that's going right in front of that blower compartment door. There's no way for me to get in there without dismantling this whole thing and doing any sort of work. That also goes in front of the return duct work, which just so happens to be where I get my filter out of there. This filter was never changed since it's been there because it's physically impossible to do so. All right, I would have to remove the washer-dryer combination, the water heater, all the gas piping, and everything else in there just to get to that furnace if I had to work on it. Not to mention, if that door is shut and I don't have any louvers on it, then the dryer's blowing air out. I'm going to be backdrafting my water heater, my furnace, if I don't have combustion air coming in there. It just has bad written in so many different areas. I have to say that with the newer condo constructions, I'm very happy to see that things are more spread out. They do bring in fresh air combustion. They are doing a lot of bringing in outside combustion air for furnaces and water heaters. So that part I'm pretty happy with. All right, a little bit on the burners. I'm not going to go real heavy. Typical manifold burners on here. Those orifices that I was talking about, they're going to be at the bottom. My device actually went dead, so I can't put a cursor on there. So where the manifold comes in there's going to be a small pinhole. That's the orifice. If I change this from gas to propane, that orifice has to be changed out as well. Larger opening for gas, smaller opening for propane. Those sliding tubes and the opening as I'm coming off the manifold, those are where I draw in my combustion air. All right, it's called Venturi tubes. So as the high pressure gas shoots in there, that creates a negative pressure around it, draws in fresh air and oxygen. These ribbon burners, typically, if they're working right, then they're going to be putting out a nice blue flame. So in the upper right corner of this slide, I would like you to look at some of those colors that are on there and just keep them in the back of your mind. Don't be surprised if you see a test questions on that. So natural gas, typically going to be blue, and there's going to be some pink or orange tips to it. LP is going to be more of a greenish tinge blue. When we're dealing with oil, it's going to be either orange-yellow or yellow-orange that's mixed in there. But most of the stuff we're going to have around here is going to be natural gas or propane. So it's going to be blue or green when we're dealing with it. Pilot lights coming on there. Sometimes we see silicon igniters. Sometimes we see pilot lights. Sometimes spark igniters. Different things that we're going to go ahead and start the fire. All right. When you hear the clicking coming out of a furnace, that's the spark igniter. This big gray box is actually what creates that and verifies that it's running. All right. Nowadays, everything kind of goes with these what I call glow plugs. So the proper term is a silicon igniter or heat igniter, hot surface ignition. All those are acceptable. When this thing starts up, it's going to glow bright orange. Then the computer is going to send gas in there. You can see the separation between the port and that tube. So the oxygen is going to mix in it. And that should ignite and getting everything lit up here pretty decently. All right. Monoport burners are found on just about every newer furnace that comes in here. All right. I hear a lot of people say that if the flame's blue, you can feel confident that it's tuned right. I think that's, when it loses its blue color, that means it's tuned really bad. All right. It doesn't mean it's tuned right. It's just not tuned bad, if that makes sense. Another furnace I'd like to chat a little bit about, and I only seen 3 of these in my lifetime. They're called Pulse. They were made by Lennox. And then, so when we have our other furnace, we have a burner going inside there. We have heat exchangers in there. We have inducer fans and pressure differentials and a whole bunch of other stuff that comes in there. All right, to make it work. What they did, Lennox did, was make a furnace using nothing but a combustion engine, for lack of a better term. In fact, that's exactly what this is a combustion engine. So it's going to send in gas, it's going to blow in oxygen, it's going to, just like a spark plug, and get an igniter going in there. That's going to explode, right, just like a car engine does. And then it's going to go up and out through the tailpipe into something called a decoupler. And I think the next slide shows that, and we'll put it up in here. So you can see at the center piece that's kind of a cone shape item. The gas and the air goes in there. We get our explosion. That's our primary heat exchanger. We get the tailpipe. That's actually number 2 heat exchanger. The decoupler, which keeps that pressure and removes the vibrating of the combustion engine. That's the 3rd heat exchanger. And then that pressure, it creates a positive pressure inside this unit. That pressure now pushes all the gases through the coils, which is the same as we had for our air conditioning coil. And they're very efficient. All right. It's surprisingly quiet, and I don't know, the people that I see that have them, the ones that are still working, they love them. All right. They were very problematic. This is where you start seeing decouplers on ductwork, because these would vibrate when they would run, just like you would feel the vibrations of a lawnmower running. These would do that, and they would rattle the entire ductwork. So they would have to put their plenum up, and then they would put about an inch or 6 inches of rubber ductwork or some sort on there. And so as that thing would vibrate, it wouldn't vibrate the rest of the ductwork in the house. And they would have to do the same thing with the return ductwork as well. That actually turned out to be a standard practice for a long time, and people were putting that in on many furnaces. But it's kind of gone by the wayside, and we don't see it anymore. And so that's called a Lennox Pulse. All right, it's literally a combustion engine. And like I said, 3 of them I saw in one house, and I was surprised that all 3 of them were working. I got to tell you, I was like a kid in a candy store, when I saw this. I'm like, oh my God, it's a Pulse. And And I saw these diagrams so many times, and I knew what it was, and I was all happy and checked it out, and everything worked fine, and that was it. And the last one was in an inspection I did in Northbrook. We actually did a training class in there as well, and yeah, that was another one. They had a Lennox Pulse in there, and nobody seems to have the same dumb excitement that I have on this stuff. So enough of that. All right. So they were recalled in 82 to 89. Models starting with GS, GSR. The reason why they were recalled, because these are condensing furnaces. They are high efficiency. They did have a high level of corrosion, which damaged that secondary heat exchanger. Again, best thing you can do, look on the floor of that blower fan, see if there's any water underneath there. And as long as there's an opening there, then it pumps out carbon monoxide, because it's a higher pressure inside the heat exchanger because of that combustion that's happening there. So it's able to pump out carbon monoxide, and that's obviously a problem. So, last thing we're going to chat about, and then I'm going to finish up here, is going to be filters. Again, I think I chatted on those before quite a bit. I can't encourage you enough to talk to your clients about the importance of changing out these filters, keeping them clean. This one actually got so dirty that it folded in on itself and collapsed. And we don't know how long this was like this, too. So remember the order of airflow, going back a little bit. Filter, fan, heat exchanger, and then the air conditioning coil. Now that air conditioning coil is, when it's running, it creates a lot of humidity because the air inside is humid. That coil is cold. Condensation is going to form on it. If I'm blowing that dirt over that wet area, that's just going to create a cake of mud. And if it gets to the point, because there's no way to get in there without dismantling everything, if that creates a cake of mud, then that's just going to stop my airflow. And now the only cure is to either take it apart and clean it, or remove everything and put a new air conditioning coil in there. Either way, it's not going to be cheap. Emptying refrigerant and putting it back in there is just not an affordable thing to do. So do everything you can to encourage your client to change their air filters. I know I sound like a broken wheel. I apologize for that. I just really think it's a minor thing, and it's really important to do that. I show them the sizes, show them the arrows, how to put it in there, especially if it's a first-time homeowner. And I try to feel the clients out a little bit if they know what they're doing. I'm not going to insult them by hounding on this. But if they're new and they got those bright-eyed looks in their eyes, then I'm definitely going to be talking with them. These cartridge filters that we're seeing more and more of, they're higher MERV. I'm hearing these things go for 6 months to a year. And I'll let them run until I get a bad temperature, rise out of these things. So, which reminds me, I'm due to change my air filter, and I better do it before Mrs. Bellefontaine gets mad at me. So, electronic air filters, they also have certain directions. There's supposed to be pre-filters and post-filters. Those can come out and either be hosed off or put in dishwashers. I heard people get good luck with that. The other ones, it's nothing but a big bug zapper. So as the dust comes in there. There is a test button typically on the bottom of these things, so that when it does run, we could press it. And if it starts clicking, then we're good. All right. Pans. The only time we do not have to have a pan underneath the furnace is when we're in a basement or a concrete floor underneath, and there's no chance of doing any damage below the structure. But if there's wood frame or something like that, or it's on an upper floor, we want to be able to collect water from the high efficiency furnace, the humidifier, and the air conditioning unit. All those items can go ahead and create water, and if the condensate drains clog up, then we need to keep that from damaging the rest of the building. So, and we have to have either an alarm, some sort of cutoff switch, an auxiliary drain, something that's going to let us know that we have a problem and some action needs to be taken when we get up in there. All right. Electric heating elements, we don't run into these too often. Sometimes you'll see them in the ceiling, sometimes you'll see them in the floor. For those of you that are going to use thermal imagers, I love to do that, especially with those warm floors in the bathrooms and such. I'll just take a picture of the thermal imager. At least we know that it's working. All right. I'm not going to get into the sizes of anything else. Most of these aren't really meant to heat a room. Some of them are, mind you, but not those bathroom heaters. Those aren't really designed there. They're designed just to keep the floors warm, and that's about it. So, all right. A couple more slides, and we're going to wrap this up. All right. We do have to have a heat source in every room. So this is something that I see overlooked when we do our field training on some of these homes. We've had houses that didn't have a heat source at all in it, and it just wasn't recognized, because if we don't see it broken and it's just not there, it doesn't really look like a problem. If they do have a permanently installed electric baseboard heater, that's fine. That doesn't mean that a portable heat source is okay. It is not. It has to be permanent. All right. Typically, there's going to be a data plate on these things. If there isn't, then we got to guesstimate it. All right. So we want to have 7 is kind of an easy number to remember. All right. 7 watts per square foot when we come in there. So if I got a 150-foot room, multiply that by 7, is going to tell me how many watts I'm going to need from this room. The other thing is going to be a general rule of thumb. And let me skip over a little bit. This again is just general rule of thumb. We're going to say it's 250 watts for every linear foot, but whatever the data plate says first. All right. These things are all designed to keep a convection loop going into the room. So the bigger the room, the bigger the heating unit, and we don't want to have anything in front of it, such as couches or curtains or anything that's going to stop that convection loop. All right. If they are going to put curtains in there, keep it up higher. These electric ones, they get hot. I've seen these things at like 300 degrees. Because they get so hot, we're not allowed to put outlets, cords, plugs, anything on top of it. All right. So if it's an after effect where it was installed, that creates a problem in itself. All right. Now I've seen them where they're installed in them. That's fine. If it's hydronic heat, that's fine. But if it's an electric radiant baseboard heat, having an outlet over the top of it is not fine. All right. Caution high temperatures, keep cords, drapes, and everything else away. It does get hot. Plain and simple. All right. And I think I'm going to stop here. We're going to, let me just see something real quick here. Yeah, just a few more slides. We'll get this out here. So when we're talking about the difference between gas appliances, we deal with BTUs. When we deal with electric appliances, we end up dealing with kilowatts that comes out of these things. There is an equation. I think it's at the very top where it talks about the difference between the kilowatts and the BTUs and the size, but we don't really get into that. We want to make sure we get enough hot air flowing and check our temperature rises. The biggest problem with electric furnaces, especially in the summer months, we have trouble getting all the burners on. All right. So electric furnaces or electric forced air furnaces, they don't all come on at the same time. There's a sequencer in there. So usually it takes about 4 or 5 minutes or more to go ahead and get all the heat going. But if the thermostat is going up and we're getting heat in there, sometimes they don't all turn on. Plain and simple. They just use whatever burners are needed, to produce the amount of heat that's needed to get in there. So they recognize the amount of heat that's coming back in the return air, and they're able to see if they need to kick on another one and another one and another one where it comes to it. All right. One thing that is different about the electric forced air furnaces, these we do change the flow of air. So if I go back a slide, oops, I went too much. The gas furnace on the right, filter, fan, heat exchanger, air conditioner. With the electric furnaces, we're actually going to put the air conditioners before the electric furnaces. So the air conditioner comes first, then the filter, then the fan, and then I take that back. First it's the filter, then the air conditioner, then the blower fan, and then the heating coils. These are thicker and they're just not worried about being damaged from the air conditioning unit. All right. This is what one looks like. Me personally, it's a 240 volt appliance that I just would not touch. All right. It's going to be easy to get one of those cover plates and touch one of the heating elements, short the whole thing out. You're going to create one hell of a problem. So really the only thing we're going to want to do is turn it on and check for a temperature height. I got nothing else here that I can give you advice on that for it as well. So just do your temperature rise and that's about it. So I'm going to end this here, and I think I'm going to do, next week I'm not going to do anything, but the next one's going to be a hydronic system that comes in there. So for those of you that stayed with me this whole time, thank you. And I hope these are helpful. And again, they're going to be, I'm posting them up on our website as well at thehomeInspectors.com. It's going to be under the education and training, or under education and employment section. And you're welcome to review them over and over again, or they'll be here on this YouTube channel as well. And so I'm going to keep working on these things. And again, thank you. And that's it. All right. You guys have a good day.